Josip and Zofia, and they will be in this same order if we run a depth first search on this tree. Okay. You are also pretty successful once we fixed our issues. Moving on. Geometry. So this turned out to be much trickier than expected. And the task was about finding the shortest path from 2 points, let's say from A to B, while also touching the given disk with some center and radius. So first, a couple of easy parts. Okay, we have a stray balloon. We'll manage. So if A or B, if one of them is located, or even both of them are located within the disk, then we don't have a problem. We'll take a straight line and that's it. It gets interesting when these 2 points are not, both of them are not within the disk. Then we first have to figure out whether a straight line solves the problem. So we'll check if this straight segment from A to B touches or crosses the disk. How do we do this? You can take the projection of the center onto this line and then figure out if it's far enough or not. Be careful about collinear cases, about cases where points A and B coincide, and so on. Any place you're trying to divide by some length, think twice whether that length could be 0. Okay, and if this doesn't solve the problem, then we have some more general case, such as the one illustrated down here. And what's actually going on, so if you imagine, we're inflating an ellipse with these 2 focal points. At some point, it's going to touch the circle. And the points on the ellipse are exactly the points that have a constant sum of distances from A to the perimeter and then back down to B. Okay, so you can imagine this. How do we find this touching point where it's tangent to both of them? You can guess, or you can prove that it makes sense to search within this angle from AC and BC. And a property useful if you want to prove this is that the normal at this touching point P will actually bisect this angle APB. So this is a property of ellipse. So if you want to be exact and actually prove this, it comes in handy. Or you can take this for granted and use ternary search because this function is unimodal in this range. You're inflating this ellipse and it's taking up more and more of the circle. So this was one solution. There's also an alternative practical solution. Sample uniformly around this circle and figure out which part is the closest and then focus on that one. So narrow down to the most promising section. If it's dense enough, you can pick that section and its 2 neighbors and then repeat this logic and you'll get this right. Okay, so we mentioned the intended solution, the alternative practical solution. There's also an exact solution where you can solve a system of equations, and I think it's a polynomial of 4 degrees, so yeah, have fun with that. We tried, it's long. Okay, so the intended solutions were these 2. Problem I, with interactive reconstruction. So we're also dealing with trees, and we have to reconstruct tree structure just by querying the sums of the neighbors. So we're assigning some values to nodes, some binary values, and then we get the result. What was the sum of values of all its neighbors? And we have very few queries. When you're allowed to do like 16 queries for pretty large trees. So how do we do this? The first idea is if we take a query with just ones, then we can figure out what are the leaves in this tree. Obviously, the nodes which will get a 1 as a result. Okay, so we know something, the green nodes. Next step would be to figure out what are the parents of these leaves. And yeah, if we could use arbitrary values, not just binary values in these queries, we could just assign different values to all the nodes, and then from the answer we could read off for every leaf who was its parent. Unfortunately, we can't do this with arbitrary values, but we can stretch them out into log n binary queries and achieve the same thing. Cool. So now we can find the leaves. We can find their parents. So we get rid of the leaves and we repeat the idea, but we run into a problem that this could take many iterations. So we have some long tree. We'll be pruning leaves for a very long time before we get to just single node. But what you can observe that you can just adjust the answers to the previous queries. There's no need to repeat the queries. As you're cutting off the leaves, you can also update the results for all of these queries that you did initially. So there's no need to redo this. So time complexity is n log n, and you do need just log n plus 1 queries to figure this out. Cool. So eventually pretty short once you figure out all the tricks. So how am I doing with time? Pretty well. Okay, cakes. So we were dealing with cakes. We had to decide which cakes to bake to obviously maximize the profit, where the profit was the selling price minus the production costs, and these production costs consisted of ingredients and the tools that we need to use to bake them. Okay, the trick was that tools can be reused, so this is a bit of a problem, but ingredients, we could just simply subtract them from the selling price and forget about them. Okay, and it's a relatively standard problem. We can model this with a graph and look for a minimum cut. So why this works? So we'll take one set of nodes that will represent cakes and the other set that will represent tools. And the weights on these edges will correspond to some loss of profit. And these intermediate edges have infinite weights. They just link cakes to the required tools. Now if you look at the cake edge, so this one, if we cut it, then this corresponds to not selling that cake. So we can take a loss of profit if we decide not to sell this. On the other hand, if you look at the tools, buying that tool corresponds to cutting an edge, and again, this is a loss of profit. So overall, if we're looking for a minimum cut, we'll get some minimum loss of profit with no existing path from source to sink. What would such path represent? Such path would represent selling some cake, so we decided against not selling it, so we're selling a cake, and there exists some edge to one of its tools such that we decided not to buy it. So obviously, if this is what we're trying to prevent, so the minimum cut is what we're looking for. Final step, be careful. You have pretty large weights in this graph, so although it's small, relatively small, the weights can be large, so just the standard Wolff-Parkinson approach will be too slow, so you can either use some capacity scaling or swap it for Edmonds carb, Dinitz, or pretty much anything else. All right. Laundry. So the task was about drying sheets, and we were given 2 lines where we can hang these sheets. They were of equal length, and for every sheet we could hang it over just 1 line or 2 lines. And if you use 2 lines, it will dry faster, but we are using up more space. So the question was how to answer these queries for different lengths of these lines. So what is the minimum drying time required to dry all of these all of these sheets? So basically you could hang all of them over a single line if they fit on, but it might take long. So the question was, how many can you afford to put over 2 lines while still fitting the rest of them on whatever remains? Okay, so the first idea is to use binary search. If you can dry something in 10 minutes, you're also going to dry it in 20 minutes. And the other way around. So if we fix some drying time t, what we can observe is that we would want to use a single line if possible. So if the slow drying time is good enough, we're going to use just 1 line. Otherwise, we are forced to hang it over 2. So, for example, these two cases, the slow drying times are 15 and 17, whatever units, and the current drying time that we're trying to figure out whether it's possible or not is 10, so we have to put this over 2, and we can use just a single line for the rest. So these two use up some space, and we are left with some shorter lines, and on these two lines we have to arrange whatever is left, and we have a Knapsack-like problem which we can solve with some dynamic programming, where we're asking or solving subproblems of the type whether we can reach some length, some fixed length d, by using the first n of the sheets that are still left to be used. Okay, so it is a solution, but it's not fast enough. So how can we improve on this? The first observation is that there's no need to do a binary search. We can sort these sheets increasingly, but their slow drying times, and just keep increasing the set of sheets that we are using in this dynamic programming. So as we're increasing this threshold, we can afford to hang more and more sheets over 2 individual lines. So we start with everything over 2 lines, and then we're changing this. And we have to figure out whether this is even possible. How do we do that? Well, we can try to fill one line, so the remaining part, to capacity. So as much as we can, because we know that whatever's left is going to go on the other one. So this is ideal. So if we can fill it as much as we can, then a very small part that's remaining is definitely going to fit on the other side. So we're looking for the maximum distance such that it's less than half of whatever was left, and that we can actually reach this distance. And the answer for some given time depends on the drying time of these slow times, and on the other side of the fast times for the sheets that we hung over 2 lines. So you have to consider both cases, and you're almost there. So the last step is to note this dynamic programming table, what you're actually computing when you're going from one sheet and then adding another batch sheet. What you're doing is basically just computing about OR of 2 subproblems, and basically just 2 parts of subproblems. So you're ORing 2 subarrays, and you can use bit sets for this for a roughly 50 times speed up. Okay, so we're exploiting bit parallelism to compute this faster. And you are also pretty successful with this task, more than we expected. Cool. Now keys. So there weren't as many solutions as we hoped there would be. So let's look at this. So the task was to arrange an exchange of keys between 2 residents on a tree structure. And some person had to go from, let's say that C0 had to go from 0 to 1, and then the other person had to go from 1 to 0, and they were exchanging keys for the edges in this tree. So you can't pass an edge if you don't possess the key, and you can initially partition the keys between the two people, and you can also drop off the keys in individual nodes. So the first part is to note that if we root this tree in the outdoors, in the node 1, if this node 1 is not part of any cycle, we'll have no solution. So why is that? The first person, Alice, will have to enter this node 1 before leaving via one of the edges, and then Bob will have to start via some other edge, because he doesn't have the key for the edge that Alice used last. So if these are all some separate trees, there's no cycle containing the node 1, then we obviously can't arrange an exchange of keys, and this just doesn't work. Otherwise, we'll show that we can always construct a solution. So how do we do this? We can just first find such cycle. We can compute a depth first search tree, and we'll find some back edge from some node, let's call it Z, back to 1. Okay, so we know that there is a cycle, and we found it. Now we'll consider a couple of cases depending on where this 0 node, so the bedroom is. It could be in this node A, in this node B, or this node C. So the first case, if it's in A, so if it's in a completely different subtree separate from the cycle, then what we can do, so Alice can go from A to 1, then it can follow the edge to Z, drop off the keys for this initial path, and then move back. So when Bob comes in, he'll take the other part of the cycle to get to Z, grab the keys, go back, and then he has the keys to travel this initial part as well, which he just recovered. So we have the first case. Let's consider the second one. So what happens if we start somewhere on the cycle? Well, this one's simple. No need to grab or drop any keys. Simply use the other side of the cycle. So Alice could go from B to 1, whereas Bob could jump from 1 to Z and then take the other part of the cycle to get to the bedroom. Now the last one, what happens if this initial node is somewhere off the cycle? Then the Alice will go from C, so it will move to the cycle, go from what? From X, no, it can drop the keys for this initial part from X to C at this node, and then take the path to 1. And then Bob can enter through this other edge from 1 to Z, then move from Z along the cycle to this node X, grab whatever was left for him, and get to his destination. So basically a case study, not too hard, but quite annoying to implement and also to test. So without some testing framework, it can get pretty tricky figuring out whether this works or not. So you can rely on your precision and submit your solution and let the judges do the work for you. And then I guess if you get the wrong answer, you're forced to do some debugging yourself. Okay. These were keys. Now let's talk about stacks. So stacks also don't need any special typical structure, so it's just about some common sense reasoning, but again suffer from the same issue that it's hard to debug and test. So the task was to sort the elements in stacks with different capacities. Well, what you can do, you can take one off the top of the stack and move it to some other stack. And to start with, we gave you a constraint. So what that constraint said is that you can empty any stack if you want. So there's enough room that you can take any stack and then reposition all of the elements to the other stacks, and you'll always succeed, even with the largest one. Cool. So the strategy is to move the smallest number, x, into place. So let's say we'll move 1 to this initial position from some source to target stack. If these two are not the same, maybe just make them different if they are the same. So let's assume they're not the same. So what you can't do is you can't clear the top of one stack and then clear the other stack and then hope that there's enough room for this to work, because there might not be. Number one could be at the bottom of one stack and the other stack could be full, and you can't clear both of them. You can clear just one. So you'll need some stage stack. So you pick another third stack where the top of that stack will be reserved for this number that you're trying to move to the destination. Okay, after this, the process is to let's clear the source stack. So whatever is above our number that we try to move, let's get rid of it. Obviously, we're avoiding this reserved position. So we can do this. So there's enough room to get rid of everything. So we can assume that in the next step, this number one is at the top. Okay, so the next step is to clear the target stack. We might have filled it somewhat in this previous one. So we want to clear the target stack, and we're trying to, so we are in this state now. So we're trying to clear the target stack and avoid this source one. So we'll use we'll use the other stacks as long as we can, but at some point we might be forced to use some of the source stack, because the source stack is basically cleared. We can't simultaneously clear the target stack as well. So at that point, you can move one. So this is the state. So we're clearing the target's stack, but we didn't succeed completely. So at this point, we can move one to the reserved position and basically free up the entire source stack for whatever is left. Great. So we can completely clear the target stack and then move one into place, wherever it was, if it was at the reserved spot or if it was left in the initial source stack, because we didn't need an extra space. Okay, so we placed number one in the correct position. So we're dealing with a slightly smaller problem, which has smaller capacity of the first stack, and we can just repeat this for 2, 3, 4, 5, 6, 7, 8, and so on. However, it doesn't work out because this needs at least 3 stacks. So if you follow this logic and you end up with just 2 stacks, you can't resort them and they might not be in the right order. So what you can do is perhaps make sure that there are always at least 3 stacks left. So you can just leave the top of each stack free and just sort whatever is below them in round 1, and then in round 2, just make sure the tops get the values that they need, using exactly the same logic. Okay, so no special data structures or algorithms, just a bit of analysis. Yeah, so now we're in the region where there were no solutions before the freeze time, so I'm not spoiling what happened after this. And these are labeled paths. So the task asked us to compute the lexicographically smallest path from a single source in a directed acyclic graph. So first, what doesn't work is a simple Dijkstra approach, where we could start with a single source and then iteratively compute shortest paths to the neighbors and so on. So why this doesn't work is what happens if you have several shortest paths, let's say at this node 4, and one of these shortest paths is AB and the other one is ABC. So one is a prefix of the other. Which one is preferable? And the answer is that you can't say. It depends on how you're going to continue this path. If you continue this path with via some edge that has label A, then it makes sense to take this AB into node 4. However, if you're going to exit it via some node D, then you don't want to continue AB with a D. It makes more sense to use the other alternative, which is ABC, and then put D at the end. So going from a single source gets tricky, and you'd have to maintain a set of shortest paths of different lengths for every node. So could work, but you don't have to do that. You can go backwards. So for every destination node, we'll compute the shortest path from the source to that node. So it's a directed acyclic graph. You can compute a reverse topological order and then do this. So why this works? If you're looking for a shortest path from, let's say, 3 to some destination 6, then you're interested in the shortest path of its direct successors. So let's say in this case 4, or maybe if there was some other node, you're interested in the shortest path from that node to the target node. Doesn't matter how long it is, as long as it's lexicographically smallest. Okay, so that's the general idea. But what we're dealing here with are paths which are sequences of some substrings of a superstring. So every edge was a substring of some superstring, and then you're concatenating these substrings, and you have to compare such paths so that you can decide what's better, going from 1 to 2 or from 1 to 3, if you know that the shortest path from 2 to 5 is ABA and from 3 to 5 is ABCA. How do we do this? So we need to compare two such sequences, and basically we can merge them. So if we look at two sequences, the first one is maybe just some substring A, the second part, so we're looking at the concatenation of this substring is maybe AB, and then it's CAB, and so on. And the other one is a slightly different concatenation. Perhaps the first edge contained 4 characters, and so on. What we can do a merge in some linear time in O of n, where n is the number of edges, or in this case, also nodes. So the shortest path will contain at most n edges, and we can just do a merge-like comparison of these two paths. Still one problem left. We have to be able to check for comparison some parts, again, some substrings of this superstring A. For example, here the first part matches, the second part matches, and so on. And then here we'll find some difference. And what we can do, so we'll have some linear number of equality checks, and then just one comparison whether this first substring is smaller than the second one. So we have to be able to compare strings for equality and then substrings, and then decide whether one is smaller than the other. And there are 2 ways of going about this. The first one is just to use some polynomial rolling hash, and then obviously if we compute some hashes for prefixes of our superstring, then we can compute a hash of an arbitrary substring, and it's simple to figure out whether 2 substrings match. Whereas for figuring out which one is smaller, we can just do a binary search for the longest prefix. So we exploit the fact that we're doing a lot of equality checks and then just one comparison that actually requires a binary search. If you don't like hashes, you think they're unreliable, you can achieve the same thing with the suffix array. So you build a suffix array of the superstring, and then you can compare substring again in logarithmic time to figure out which one's smaller, and also do equality checks the same way. So in the process of building the suffix array, you'll compute some equality classes for substrings of different lengths, which are powers of 2, and you can exploit this for equality checks and then for comparison as well. So it's a pretty standard application of suffix arrays. All right. These were the paths. Now, attendance. So what we're dealing with is a stebbing set problem on a dynamic set of intervals. So let's first solve the problem for a static set. So if we're just given a set of intervals, and we need to figure out what's the minimum number of lines, vertical lines, stebbing lines, such that we stab every interval. There's an obvious greedy solution, and we'll want to do the stabbing at the earliest endpoint. Does it make sense to do it before? You can always move it further, and you can't afford to do it later because you're going to miss the first interval. So that's a greedy solution. So you sort this by the endpoints, and then you can solve it with a single pass. However, the problem has a dynamic set of intervals, and we're going to approach this so that we'll try to simulate this greedy process. So every time we do a modification, we're going to simulate the greedy process, but obviously we can't do this in a straightforward way, because we might have to move over all n of them. So what we'll do, we'll cut them up into blocks of size square root of n by their endpoints. So perhaps this black part is the first block, the blue part is the second block, and the green part is the third block. And we'll pre-compute the results of this greedy simulation within a block. So if I start at some interval, where I'm going to end up and how many jumps or cuts I'm going to make to end there. So for every interval within the block, we'll compute what's the end block within this interval. So then we have to jump between blocks and within blocks. Okay, To do this, what we're interested in, we are interested in the minimum endpoints among those with sufficiently large start. So if we are at some interval, we know that we stabbed it here, then we're interested in intervals that have sufficiently large start, larger than this cutting point, and we're looking for the one with the minimum end. And to do this, you'll need some tree-like structure or some binary search. So what you end up with is a time complexity of n square root of n times log n. So for every update, you have to recompute the entire block. So all square root of n for all square root of n of these intervals within the block. And you have to do this n times because you're adding things, and every time you have to simulate this process, which also includes jumping over square root of n blocks. And each job actually consists of a query like this, which comes with a log n time complexity. So this goes in the right direction, but is too slow. So we need to improve. And the improvement comes from exploiting known coordinates. So we know ahead of time what are the coordinates of the entire problem, so we can exploit this. So for every interval, we can actually pre-compute what's going to be its next interval. So this could be still an inactive interval, but we can process this later. So this pre-computation allows us to enable and disable these intervals and update this suffix minimum query data that we relied on previously with the log n complexity, now faster. So this way we can get to n square root of n time and space and end up using too much memory. Not just this, it's also going to be too slow. So this was actually a hint that you're looking for something with a small amount of memory, which is also more efficient, cache efficient. So how do we cut down on space? So the last improvement is that you can process these queries. Let's call them different times. So if we say that every interval appears at some time, we're actually processing queries at different times, which include the intervals that appeared until then. And what we can do is we can process them in parallel from block to block. So it makes sense to sort the intervals by start points, so just a helpful note. And what we'll do is for every time unit, we'll compute the end interval within that block in this unit. So first we start with the first block, and we'll compute that, oh, at time 3 we end up here, at time 8 we end up here, and at time 20 we end up here, and maybe for all the other times we end up way off to the left somewhere at infinity. And then when we try to move from one block to the next, so when we try to extend these solutions, we have to pre-compute these next values just between these two blocks. So we can end up reusing some linear amount of space when going from block to block and updating these values. So we'll use up some linear space, and the time complexity is still going to be n squared of n. Now, this is sufficiently fast to solve this task. All right, so if this wasn't hard enough, we have one more. And this was phylogenetics. The task was to count colorings of a bit special graph, which is kind of a tree, but not just a tree. So it's a tree with its leaves connected in a circle. So if we draw some planar embedding of this tree, we're also going to connect these leaves in a circle, and we have to figure out a way to count the colorings of this tree with some fixed number of colors. First off, we're going to try to decompose this graph into a tree and a cycle because it's easier to deal with trees. And yeah, how we're going to do this? First, we're going to compress the nodes of degree 2. So nodes of degree 2 are definitely some, let's call them inner nodes. We can get rid of them. So what you're left with is also known as a Hallin graph. So every node has degree at least 3, and there are no nodes of degree 2 but you also have to keep track that these nodes of degree 2 shouldn't be on the perimeter. Okay, so we simplified this, and we're still left with decomposing this into a tree and a cycle. First, we'll guess one possible route. There are not too many options. I mean, we could route this tree at any inner node, so we'll try to figure one out. If we pick one node of degree 3, plus all of its neighbors, one's definitely going to work. So we can try this, or if there's a node which has a higher degree, we can also prefer that one. It's definitely going to be a possible route. Okay, so once we fix the route, we can try compressing this graph from leaves towards the root. How we do this is by noting that triangles will only exist on the perimeter. So here you have a triangle on the perimeter, here you have several triangles, and we'll be compressing this and simplifying the structure towards the root. And if this works out, then we know that the structure of the graph was okay, and we can also reconstruct which nodes were on the perimeter and which nodes are inner nodes. And we can do this in linear time because we're mostly dealing with nodes of degree 3. So we'll be picking nodes of degree 3 and simplifying this structure. The first reduction that we can do is this one. So if you have some like fan-like structure, if you find a node of degree 3 such that its neighbors are also of degree 3 and have some common parent, some common node, then we can just drop this one out, and we know that it's an outer vertex, and we'll simplify the structure. So this takes care of nodes like these two. Now, there might not be any such nodes left. Then in this case, what we'll do, we'll take a triangle like this and just compress it into a single vertex. So take all 3 nodes. So if you have 3 nodes of degree 3 so that they're all connected in a circle, we'll compress it. But this time, we don't know whether this is an inner or outer node or which of these are inner or outer nodes. But once we're done with the reconstruction, when we're undoing these changes, we can compute these values. So if I do a compression and then figure out later on that, oh, this neighbor is an inner node and the other 2 are outer nodes, then I can also assign status to this and these 2 nodes as outer nodes and this one as an inner node. And this process will end up in this final configuration, which is a K4, and the root is the only inner node and the other nodes are outer. And from here we can undo these reductions and assign statuses to all of the nodes in the graph. So this way we figure out what's on the inside and what's on the outside. Okay, first we'll construct a cycle from these marked leaves, and we'll also reorder the children in the tree so that they're consistent with the cycle. So we end up with a structure like this. So we have a tree, and we know that we have a cycle that's connecting the leaves in exactly the order that we would get if we ran a, I don't know, depth first search. Now we have to count colorings of such tree structure which with its leaves linked in this circular fashion, and we'll use some dynamic programming for this. So suppose we want to color subtree of X. Let's say this is the top node, and we'll use 3 colors, C, L, and R. This means that we want to color the root with color C, and the leftmost node with color L, and the rightmost leaf with color R. So we need the leftmost and rightmost color so that we can take care of transitions between leaves. How do we do this? We'll have to combine some sub-problems. So how to color the first I children so that they will end with the right leaf of color D. So in this case, if I'm interested in how to color this subtree of X so that the leftmost leaf is green and the rightmost is blue, when I'll be recursively solving the problems for all of its subtrees and then combining these results, I'll be interested in how many ways there are to color the first children so that, okay, they start with the green one, but they end up with the orange one. And then I have to choose the colors of this node I and the leftmost and the rightmost node. So basically, we have a pretty large state and not so tiny transitions between these states. But we can actually improve this, so we can improve this to n k to the power of 4 by using some cumulative sums for these subproblems. So in most cases, we're interested in summing some subproblems over all values of some color which are not equal to, I don't know, red. So for this, we can compute the cumulative sums and then just subtract whatever it is that we don't like. So we're making improvements, but we're not even close. So the final step here is to note that the exact colors don't matter, just their equivalence classes. So the number of ways of coloring these three X, so that the leftmost, the X is colored with number 3, the leftmost node is colored with number 5, and the rightmost node is colored with number 3. It's exactly the same as if these colors were 1, 2, and 1. Okay? So this brings it down to a constant number, linear number of states that depends just on the number of nodes, but not on the number of colors. So we have a linear number of states and we have a constant number of transitions to consider to solve such subproblems. All right. So basically, 2 problems in one. First one, to decompose this nasty structure into a tree and the cycle, and the other part to compute the coloring. All right. So this is it. We'll take some time to prepare for the award ceremony that I know you're all anxiously waiting. So we'll continue at 6 if we don't have any delay. Thanks.
official start of the closing ceremony of CERC 2023. First, you will enjoy some speeches, then you will enjoy some more speeches, then you will enjoy the scoreboard, and then you will get prizes. Let's start. First, I would like to welcome to the stage the Vice Dean of the Faculty of Computer Science and Informatics that hosted this event. Thank you.
Thank you. Don't worry, I won't be long. So let me say for the start that it was a pleasure and great honor to host Central European Regional Programming Contest here at University of Ljubljana, Faculty of Computer and Information Science. We are proud to say that we hosted this great event now for the third year in a row. Next, I would like to thank you, the students and the coaches that attended this great competition, for your enthusiasm and dedication. It's wonderful to see such passion and commitment. Also, let me congratulate to the teams who are advancing to World Finals and wish you the best luck in the upcoming competition. There is no limit to what you can achieve. Finally, yet importantly, I would like to thank the organizers and sponsors whose collective effort and contribution made this amazing event possible. Let me mention that most of them have been part of the contest organizing teams since 2021. Thank you.
Thank you for the speech. Next, we would like to welcome the Vice Rector of the University of Ljubljana, who came to here and will be distributing prizes later, Professor Dr. Anton Ramšak. Next up, we will hear from the General Secretary of the ACM, the Association for Computer Machinery of Slovenia, Filip Koprivec.
Hi, so some warm regards from the Slovenian ACM chapter. It really fills me with joy to see all of you here. Competitors, congratulations. I hope you had fun here in Ljubljana. I hope the contest was rewarding, and I hope it did pose some challenges. And judging from the Tomáš's presentation, you did have some challenges to solve. So I hope that was fun. Nevertheless, this competition couldn't be possible from the people that supported it. So most importantly, the sponsors, you'll hear from them a bit later, and from the Faculty of Computer and Informational Science, thank you for lending us your space, and thank you for hosting us. Nonetheless, the most important thing behind the competition is the one that you hope to never see, and that is the Technical and Scientific Committee. And I would like to single out Jan Berčič and Jure Slak for making sure that Putka worked, and you were able to submit everything, the grader was able to judge everything, and the checks were able to come to you and fill you with joy to see that you finally solved the task you had meant to be solving. Thank you, Jure and Jan. And since Jure and Jan were not willing to stand up, Tomáš, please. You've been organizing this for 3 years. This is the third iteration of this regional contest in Slovenia, and I know that the team has worked really hard. So thank you, Tomáš, again for making this possible. So yeah, that's it. Thank you.
Next up, representatives from the higher levels of the championship. Dr. Boba Manova. Yes, thank you. Please.
is there somebody who didn't listen that 3 teams go for sure for finals, and 12, I have already a list of them, go to European Championship. So I hope I will see you there in Prague in March 24. See you. Still there is an empty place for next CERC.
Thank you very much. A video from Jane Street.
These competitions help to create and empower a new wave of talents and leaders in digital technology, and they help to grow a new generation of future programmers.
The competitive programming community is special to me just because I grew up with it. I started doing this when I was 12, and it basically kick-started my whole career.
I think it's important for Jane Street to be supporters of ICPC community because this community is very important for development of many young people who just started their journey with software engineering.
What makes ICPC special to me is that people from many different countries just come together to one place to compete against each other and create a community.
Many Jane Streeters have been involved in the same competitions you're here to take part in. I met some of my closest friends through these competitions, and to this day I still enjoy solving problems with them.
I have been competing in ICPC for 10 years. It was what introduced me to the world of programming, to the world of problem solving.
My experience at ICPC prepared me for my role at Jane Street, mostly in terms of being able to formulate my ideas clearly and implement them quickly.
I use a lot of programming skills I learned during my years in ICPC competitions.
I think Jane Street is kind of similar to ICPC in a sense that we solve a lot of complex and interesting problems in a very quick matter. And I think this experience led to me being successful in my career and having a lot of expertise in what I do.
This is how I've met a lot of friends in high school and in university. We participated in competitions, we share a passion for competitive programming, and now we work together at Jane Street.
You're surrounded by people who care about the same things as you. If I could give advice to someone competing today, I would say make as many connections as you can.
The most important part is to find your friends, gain knowledge, and have fun.
And now from JetBrains, Julia Bobovic.
Thank you. I didn't do anything, thank you. Hi, it's Julia. I'm back with my lightning speech. I'll try to make it shorter than the first one, because we all know what we're here for. It's not to listen to me. I would like to congratulate every one of you I think just being here is a great achievement, and we at JetBrains acknowledge all the hours and all the hard work you put into just being here. So I would like to give a message to those who do not get a prize today or do not get the medal they were striving for, which is, as we all know, we don't really have free will, and a lot of our life is just chance and luck, so better luck next time. Yeah, and a message to the medalists. If you could come to our booth after the ceremony is over, we will give you some extra prizes from JetBrains. And I would also like to once again thank you, the organizers of this event, ICPC organizers, local organizers. Thanks for the great job you do. And yeah, I hope all of you had fun at this competition and made new friends. Yeah, much love and respect to all the participants and coaches. Thank you.
The kind words, and now we'll have a promotional video from Huawei.
Maybe patience. I think it's adventure.
I think it's dedication. It's dedication and also loving to solve problems.
Be able to put in the hard work to study and prepare for this competition.
It's hard work.
It is effort.
There is a lot of smart people in the world, but few of them are persistent.
Hi, I'm Ignacio. I'm 21 years old.
My name is Mateus Aires. I am from Brazil.
My name is Xu Wen. I'm from Zhejiang.
My name is Bernard and I'm from Iceland.
My name is Zhen Zihao. I'm a grade 3 university student from Tsinghua University.
My name is Masataka Yoneda.
My name is Hirotaka Yoneda.
You're at the ICPC Challenge Championship powered by Huawei. We are facing huge challenges, just waiting to be solved by best of us.
The business of helping people prosper, for there to be enough and more than enough.
I'm excited to see what will Huawei bring us next.
I am very excited for the contest.
I'm excited and a little nervous.
I feel a little nervous because it is the first time in this year to participate in a big contest.
I have the experience to get second place in international optimization contest.
I also aiming to become top 3.
I think I will get into the top 10 because I get the top 10 in the previous content.
These type of challenges are really hard.
When I join a competition, I don't like to lose. I usually join to win. I want to come at first position.
Mostly known for 5G and like internet related stuff. But we got to know that they're also doing like some solutions for car, and I found that quite cool.
There are a lot of high technologies in Huawei.
They have a lot of products over all sorts of businesses, and it's a very large company.
I thought that they are doing for the scientific innovation for the society.
We see that Huawei is very committed with doing better, with improving and with innovation.
Because Huawei is a name that people trust to provide their communications and services. And that's actually why I'm right here at headquarters in Huawei.
I made the result a bit better of him.
I finally got 30th place.
Not very well. I got the 18th.
Today I got 14th place, and I think I'm satisfied with that.
I won the competition. I was first prize because I got some recognition of some very good people, so I was happy about that as well.
Huawei problems are really focused on real life, so I think it will help people in the future.
The problem is buffer sharing and reallocation problem. One of the bottlenecks of computer speed is about memory. So, what happens if computer speed is going up? Not only our computer becomes faster, we can do many research.
It can improve self-experience of using cloud services.
We're doing it together with industry and community leaders in the small and in the large. And I think that's one of the reasons why Huawei loves to be part of the competition. So we have training camps in a lot of different ways, and actually Huawei sponsors some of those training camps. And also challenges where we introduce problems that don't fit the ICPC model of competition. The ICPC is about creating opportunity for others. That's what I mean by flourish.
Congratulations to all the contestants and coaches for this successful event, and wish you all have the best result in today's contest and in future's contest in next year's World Final. And for Huawei, we will continue to support various kind of contest with contest community together, and we are going to develop more and more platform and opportunities together with contestants and our regional community. For example, you see this year we introduced Huawei Championship, mainly HQ in China, and here in Europe, we are expanding and developing a local tech platform brand named Tech Arena. You may see some materials we already shared at our booth. So we welcome for any scenario and any approach and any ways to seek for deeper and further cooperation with the young talents, with the coaches, with professors and the universities to work together, push the technical development of this era ahead further and more. And in any of the occasion, if you meet Huawei, we welcome you to have a conversation with us for any kind of topic if you are interested, for any kind of technical topic and any kind of social development topic. We'd like to work together with all you in future. And generally, thank you very much, and congratulations to everyone for today's this competition. Yeah, good luck. Thank you, everyone. Yeah.
Also like to thank our other sponsors, Pinely with their popcorn, and the Slovenian Association with Informatics and Telecommunication. Also, we would like to thank Visit Ljubljana for sponsoring the food, right? At least the food, yeah. Okay, next. Next, Tomasz is coming back up to reveal some statistics about the contest.
Okay, so we'll keep this short. Oh, here's the clicker. So some interesting statistics without spoilers for now. First off, some number of submissions. So before the freeze, we had almost 500 submissions. Out of these, 230 were correct. Well, after the freeze, we had a significant amount of submissions. However, the ratio was a bit lower as you were tackling harder tasks, obviously. So we handed out 240 balloons and 250 printouts, at most 13 per team, so this is not as much as last year, so I hope you had less debugging to do than last year. And you managed to produce over 30 gigabytes of home directories, which were stored just in case something burns down. All right, some special mentions for the first task that was solved. So this one was solved by our local team, Ljubljana 2, in about 8.5 minutes. Obviously, the easiest task equals schedules. So next special mention goes to the shortest solution, again for equal schedules, this time by team FI Muni 3, which is, I think we should be precise here, 436 bytes or 22 lines. And the final special mention goes to the most persistent team, which was University of Wrocław 4, with 17 attempts on problem G going to the moon. Okay, so although I mentioned that after the freeze the success rate was not as high, there was a lot of accepted submissions in the final minutes, even in the last minute. So I think the revealing of the scoreboard will be very interesting. Here we are, so some statistics on the number of attempts and solutions, and we've already went over this during the solution presentation, and we're not spoiling who solves the hard tasks. So some dynamics. So initially, so here's a cutoff when we froze the scoreboard. So initially you were all solving the easiest problem, then so this was problem B. And the situation between the number of submissions and the number of accepted submissions is pretty similar. However, when we move on to the development in the final hour, we can see that there was a large spike of attempts. However, not all of them were successful. So especially the last 2-3 minutes are really popular. Okay, so initially, problem E, the easiest one, and then the second easiest one. And then it took you some time to figure out that this geometry is not actually as hard as it might appear, but you figured this out successfully as well. Here we go. That's it for me.
Well, I promise I'm trying to close this. Okay. 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 Okay, I won't touch anything. So, we will fast replay until the frozen scoreboard, and then we'll open from the bottom. Okay, smooth. So for now, we see University of Warsaw 5, Zagreb 1, Wrocław 1, Warsaw 1, and so on, and 9 problems in the top place. Okay, do we see row 60? Okay, perfect. So we will go a bit faster until the teams have 5 points, and then we'll go a bit slower. Let's see if team Never Touch Grass solved any problems. They attempted problem A. Nope. No. Problem E. No. And then B, C, G, H. Congratulations. (57G). Well done. 57D, H. 57L. 55H. Oh, sorry, B. No, what? I'm blind, sorry. 55B, H. Well done. Okay. And we're going to place 49G. Not successful. Okay. We continue from 48. We left Chenda. H. Well done. Problem G with 2 attempts. Problem H with 2 attempts. 47, problem B with 2 attempts. Problem H with 1 attempt. Well done. University of Szeged, problem G with 6 attempts. Not successful. Problem H. Well done. Team AA with 2 attempts. No, We have Maribor 1 with 3 attempts at problem H. Well done. Two tasks to reveal from team from the Charles University. Problem G, problem H. Well done. From the team with the smallest solution, we have problem B. Nope. Ljubljana 2, did they manage to solve problem G? Yes. NCU2, problem G with 2 attempts. Problem I with 2 attempts. Nice. Charles 2, 6 attempts at going to the moon. Nope. Problem J. Yes. Jagiellonian 5, 6 attempts at drying laundry. Nope. And 2 attempts at labeled paths. Also no. We have University of Wrocław 4, 5 attempts at drying laundry, 11 attempts at going to the moon. Most persistent team with 17 attempts. Did they manage to solve the problem after that? No. 1 attempt at L. Also no. Team E. It's called barcode. Team barcode. Okay. 1 attempt at problem K. Nope. Ljubljana 1, 3 attempts at going to the moon. Successful. Ljubljana 3, also going to the moon. Successfully. And now we scroll a few places. With Ljubljana 1, attempting keys. Nope. Then we have the team with 1 attempt at phylogenetics, which was not successful. We have LU2 with problem I, which was successful. Then we have key K. Nope. We have 1 attempt at problem G. Okay, 4 attempts at problem D. We have 2 attempts at problem I from Cactus. Well done. We have 2 attempts from the team Traktoristi to going to the moon. Nope. Charles 1, 3 attempts at drying laundry. Well done. From Wrocław 5, 4 attempts going to the moon. No. 8 attempts at keys. No. From Warsaw 2, 1 attempt at cakes. Correct. We have 2 attempts at drying laundry. 2 attempts at G, going to the moon. Also no. Zagreb 2, 2 attempts at drying laundry. 1 attempt at jumbled stacks, which was also incorrect. 2 attempts at going to the moon from Jagiellonian 4. And 3 at keys. Correct. One attempt at drying laundry from Jagiellonian 3 and 1 for keys. We have 1 attempt from Charles. No, we're stopping. we have revealed all teams with 4 solved problems. It is time to call to the stage the winning teams of the countries that have so far been determined. The prizes will be, well, the diplomas will be given out by the regional contest director, Andy Brodnik, and the general secretary of ACM Slovenia, Filip Koprivec. In place 27, we have the top team from Slovenia, Ljubljana 3. Yep, okay. So we're starting with the names I can't pronounce. It will get increasingly more difficult. I practiced, please forgive me, it will not be good. But for now, Ljubljana 3, Domen Hočevar, Jon Mikoš, Mateusz Miščić, and their host, Tomaž Hočevar. Congratulations to Ljubljana 3 for being the best Slovenian team. Next, in 23rd place, we have the best team from Slovakia, Traktoristi, Comenius University Team 2. Welcome to the stage. Team Traktoristi, Viktor Balan, Jan Priner, Michal Tkačik, and their host, Filip Kerak. Coach. Okay. Now those two will stand there for a while, and we'll continue with place 17, Charles University in Prague, problem I. They have 1 attempt, and it was successful. We've seen Cactus before. 1 attempt at problem J was not successful. Congratulations on 17th place. And then in 16th place, we have Jagiellonian 4. And in 15th place, we have University of Warsaw 2 with 7 attempts at going to the moon. Well done. In 15th place, we have Zagreb 3, 2 attempts at drying laundry. Correct. In 15th place, we have Ruhosh Alat from LT3 with 2 attempts at drying laundry. Not correct. Congratulations on the 15th place. In 14th place, we have Charles University in Prague 1, 2 attempts at jumble stacks. Not correct. University of Warsaw 2 is in 13th place. In 12th place, we have the FI Muni 1 with 3 attempts at cakes. Oh, that was a compiler. 3 attempts at cakes. And 1 attempt at keys. Also incorrect. I believe that's the top Czech team. Please come to the stage. Congratulations to FI Muni 1, Daniel Ilkovic, Tomáš Mahacek, Michal Stanik, and their coach, Nikola Beneš. Thank you to the General Secretary. Now we will wait until place 9. Place 9 is the first place that gives bronze medals. After place 9, you also get prizes from Huawei. But first, place 11, Zagreb 3, 6 attempts at jumbled stacks. They were correct, and they go on to 5th place. Place 11 is still not determined. We have 2 attempts from University of Warsaw 4 at cakes, and they were not successful. We have 4 more attempts at keys, and 6 more attempts at labeled paths. Also not correct. Congratulations to reaching the 11th place, University of Warsaw 4. Thank you for the helpful hint that I misunderstood. Well, 4th place. Sorry, what? 4 attempts at problem D, 10th place, University of Wrocław 2. Correct. Congratulations. University of Latvia 1, 3 attempts at keys, and they were correct. One attempt at going to the moon from Jagiellonian 2. Correct. We have Jagiellonian teapots in 10th place with 5 total unsolved tasks. Can they solve phylogenetics? No. Going to the moon, problem G. That is correct. We have Ilte 1, 5 attempts at problem J. Incorrect. 3 attempts, problem K. Correct. And I believe we've determined the 10th place, University of Zagreb 3. Next we have University of Wrocław 2, 2 attempts at keys. Correct. And now we come to the spoiler. We've determined place 9, University of Latvia. University of Latvia, team 1. Walter Kalninš, Matis Kristinš, Kristianis Petrucena, with the coaches Eugenis Vichros and Peternis Paklans. Pakalans. To give out prizes, we have the Vice Dean of Faculty of Computer Science and Informatics, and our regional contest director. Also, we will start at 9th place. We start with prizes from Huawei. So contestants, I don't know what will be the procedure. You get medals, you get diplomas, you get the gift, you take pictures with everyone, and then you leave for the next team. So University of Latvia, team 1 got both diplomas for the top team of Latvia and medals for 9th place along with the prizes. Thank you. Now each place obviously gets prizes, so each place will be called down to the stage. Okay, one click. We have one submission at problem I from Jagiellonian 2, which was successful. And the Jagiellonian teapots come back with another submission at problem I, 3 remaining in total. We have a success. With this, we've determined the 8th place that goes to Team LT1. Yep, please come down to the stage. Team LT1 from Hungary with Peter Gimeshi, Aaron Nosai, Peter Varga, with the coaches Laszlo Nikazi and Zolt Nemeth.
Just the diploma. Congratulations. Thank you.
Congratulations to Team LT1 from Eötvös Loránd University for being the best team from Hungary, winning 8th place and bronze medals. In 7th place, we have University of Warsaw 1 with 2 attempts at problem J, which were not successful, but they have 1 remaining attempt at problem K, which was correct. And next in 7th place, University of Wrocław 1 with 1 attempt at problem J, also correct. Then we have Zagreb 1. Did they manage to solve the going to the moon? No. But did they manage to solve problem K, comparatively much harder problem? Of course they were. With this, we've determined place 7. University of Wrocław, team 2, please come down to the stage to collect your prize and certificate. Congratulations to University of Wrocław, team 2.
Adam Ciężkowski.
Adam Ciemskowski? Ciemskowski? Jan Vankowicz and Artur Krzyżinski. Okay. With their host Paweł Gawriczowski and Bartłomiej Dudek and Krzysztof Loris from University of Wrocław. Congratulations to Wrocław 2 for winning the bronze medal. Place 6, we have Jagiellonian 2 with 1 attempt at problem L, which was not correct. Come down to the stage. Sixth place is the final bronze medal. Yes. Welcome team Jagiellonian 2, Justyna Jaworska, Jan Klimczak, Rafał Pizik, with their host Lech Duraj and Krzysztof Potempa. Congratulations to Jagiellonian Team 2. Also, thank you to Vice Dean of the Faculty of Computer Science and Informatics for distributing the bronze medals. We would like to welcome the Vice Rector of University of Ljubljana, Professor Dr. Anton Ramšak, to give out the silver medals. We have place 5. We meet Jagiellonian teapots again with the attempt at problem J. 1 attempt. It was correct, and they jumped to second place. With this, the place 5 is determined. University of Warsaw 1, please come down to the stage. Congratulations to University of Warsaw teammates Jan Kwiatkowski, Michał Staniewski, Kamil Zwieszczowski, with their hosts Krzysztof Dix, Kacper Kluk, and Rafał Sikorski, and Marcin Smulewicz, and its coach, not host again, I'm sorry. Congratulations. Congratulations to University of Warsaw Team 1 for winning 5th place and a silver medal. In 4th place, we have University of Wrocław 1, 2 attempts at problem K. Successful. Congratulations, that leaves Team Zagreb 1 in 4th place. Please come down to collect your prize. Zagreb 1 is also the best team from Croatia, with teammates Dorian Lendvaj, Krešimir Nežmach, Patrik Pavic, and their coach, Krešimir Malnar, and coaches Krešimir Malnar and Ivan Paljak. Congratulations to Team Zagreb 1 for winning 4th place and a silver medal and being the top Croatian team. And now for the Polish trio on top, we have universities, Jagiellonian University in Krakow, University of Wrocław, and University of Warsaw. Jagiellonian teapots, they had 5 problems still open when we first saw them. 1 was incorrect, 3 were correct. The final one, problem L, was also correct, and they win 10 points. With this, University of Wrocław 1 is fixed in 3rd place. Please come down to collect your prize. Congratulations to Team University of Wrocław 1 with Krzysztof Boriczka, Antoni Buraczewski, Łukasz Pluta, and their coaches Paweł Gawriczowski, Bartłomiej Dudek, and Krzysztof Loris. Congratulations to University of Wrocław Team 1 for winning the 3rd place and the silver medal. We only have, well, 2, but 1 really, remaining box to reveal. University of Warsaw 5 has made attempts at problem L. They made 2 attempts, and if successful, they would get, even if they submitted in the last minute, they get 5 hours and 40 minutes of penalty time, which would put them at 20-ish hours, 10 points, 20 hours would be before Jagiellonian Teapots. And their attempts at problem L were not successful. So we have our 2nd place, University of Warsaw 5. Congratulations to Arkadiusz Czarkowski, Bartłomiej Czarkowski, Tomasz Nowak, and their coaches.
It's okay. Cool.
Congratulations to University of Warsaw 5. How do you choose the team numbers, by the way? 5 won the best place in University of Warsaw with 9 points, and the comeback from 10th place all the way to the top, Jagiellonian Teapots Jagiellonian University in Krakow. Please come down to the stage. Congratulations to Antoni Długosz, Kacper Paciorek, Kacper Topolski, and their host Lech Duraj and Krzysztof Potempa. As an interesting mention, we also had a parallel contest running where our sponsors were competing. Jane Street would be in place 8 with their team, and the JetBrains team solving in Kotlin would be in place 9. But yes, the main point was congratulations to the Jagiellonian Team 1, Jagiellonian Teapots University in Krakow, for winning the grand prize, the Grand Cup. Congratulations at being the only team to solve 10 problems. Big round of applause. Andy is Hungary. You have to say some closing remarks. But yes, thank you to Vice Rector of University of Ljubljana for distributing the prizes.
So maybe I could say a few words. So thank you very much for coming, and I'm very glad to see so many young people, so many successful and enthusiastic. So thank you.
Yeah, the winners of the medals, don't forget to stop by the JetBrains booth for extra prizes. And now, closing remarks from our General Director of the contest. General, just from our General.
No, General. Just
From our contest director, Andrej Brodnik, please take the mic and finish off the closing ceremony.
ice cream. I like ice cream. Don't you like ice cream? Well, unfortunately there is no ice cream in the banquet upstairs, but I hope. Oh, you have teams. Okay. This is much more important and much better news than listening at me. Please, Boba.
Okay. I was trying to make it as good as possible. Maybe I have some. It's not official. Official will be tomorrow. So congratulations for 3 teams which go to finals. It is Jagiellonian University Krakow, University Warsaw 5, and University Wrocław. In the model of 3 teams to finals, there are others who are going to European Championship. Zagreb 1, Budapest, ELTE 1, Latvia 1, Zagreb 3, because we have 2 teams. If there are 2 teams in 10 and they are not going to finals. Masaryk University, Brno on 8th place, Charles University 9, Czech Technical University 10th place. On 11th place we have a Comenius University, but I didn't take 12 and 13. I will check it later on because there are no results. If you will show me, I will tell you. In case there will be 4 teams going to finals, so you know what is the result? Zagreb will have only 1 team in the final, in the European Championship. I'm sorry for this. But okay, this is very unofficial, but all of you are welcome in Prague, and see you. Thank you.
Just to clarify, did I understand correctly that 4 teams will be going to finals? 3 to finals, and 13 to European? And if 4 go to finals, then Zagreb will obviously go to finals, and only 1 Zagreb team will go to European Championship. Okay.
Seems to be that Ljubljana team is going to the European Championship.
We'll announce the official results of who goes to the European Championships tomorrow when it's fixed.
Boba, thank you very much for your quick computation, and let's leave our contestants in a little of despair until tomorrow, actually, when you will be announced the final roster for the European Championship. Okay? Thank you very much. What? Second floor? Yeah, the second floor. Before we go to the second floor, I would like to thank once more for the whole 3-year service. And I will start from the leadership of our university, Professor Ramšak, who is representing our rector, Professor Majdiš. Thank you very much for putting so much importance on our activity. We appreciated this a lot. Thank you also, faculty of the Computers and Information Science, for hosting all 3 years of events, even the first one when we had a virtual event. But anyway, I hope you enjoyed it as well. Thanks go on. I mean, it's like Oscar awards, you know, but I have to say thank you to the whole team in the blue T-shirts, the technical team, the scientific committee, because without that, I mean, there will be no competition. You can replace the regional, the contest director, that's not the problem, but you can never replace the scientific team and technical team, and all the volunteers which are here. Please applaud them. When I'm looking at these young faces here and at their success, I'm kind of envying you, because you have so much in front of you, so much open space, so much interesting challenges to fulfill and to trace and catch in the future. And thank you very much to come to Ljubljana, and we hope that Ljubljana will remain in a good memory for you, and even if there was something not completely okay, please forgive us. We did try to do our best. Thank you very much for coming. Thank you to the coaches and to everybody who was here. And I invite you 2 stairs up, right? Where is the banquet? And thank you once more. Oh, there is another slide missing. This goes the same way as announcement of the yes, in the 24. It's not clear yet, but by the end of the year, the coaches decided to, by the end of year, we have a couple of candidates, but you know, not to put too much hope in either of those. By the end of year, we hope to come up with the solution and with a place. And thank you once more, and go 2 stairs up. Thank you.